All right, hello. Sorry I can't be there right now. Owen was in our 6-month-old baby. Owen was in the hospital from Tuesday to Sunday, and so I've had a few things on my hands. Hopefully I'll be back in class for Wednesday, and hopefully I'll also be there for office hours on Tuesday. But I'll keep you posted if anything changes. For this video, hopefully you're mostly in class together. We'll go over where we were at before, and then I'll see if somebody can present problem 6.9, which was assigned in the last daily homework. And also I'll have a few problems for you guys to work on in the middle of everything. And I apologize, I don't really have time to edit this video much, so there might be some ums and ahs along the way. But it depends on how much effort you all put into understanding what all is talked about during the group work, as far as whether the group work and the video fit within the time frame of the class. So you might finish everything before the official time is up, or it might go past the time, and then you'll need to finish the video on your own on perusal. I encourage you to try and ask whatever questions you might have on perusal. You can make whoever is pausing the video, you could make them post a comment for all of you on the video, or you could post an anonymous comment on the video if you really want to, but I would encourage you just to have the video stopper just put your question there. But of course, I want you to answer each other's questions as well. So hopefully whatever questions you put on perusal are questions that you all in the classroom could not answer with each other's help. So really help each other out here, and we'll see how we do. So one of the loose ends that we had from last time involved normal subgroups. So just a quick reminder that normal subgroup, what we do is we look at its cosets. And if the left cosets match the right cosets for all of the possible elements in G, then we have a normal subgroup. And so we write it with a triangle instead of like a less than or equal to arrow. And so we went through some things about normal subgroups. You're proving some things about normal subgroups. One thing about normal subgroups for your final project that's due at the end of the week. And we ended up at that the normal subgroupness property, however you want to talk about it, is not transitive. That you could have S, the subgroup generated by S, which has these elements. That is normal in the other subgroup listed here. I'm going to end up highlighting everything, I apologize. So this other subgroup, it's normal in that subgroup. And that subgroup is normal in all of D4. But S, as you'll quickly discover, is not normal in D4. And so if we look at the group work that you guys had, at least one group had from last time, let's see here. Sorry, it's a little bit dark. They had a really light marker, so I had to make it a lot darker here. They were looking at, okay, well, is S normal in R2 and S2, the subgroup generated by, I guess not R2, R squared and SR squared. Make this a little bit more readable there, SR squared. And so they went through and they said, okay, we have S, and if I multiply on the left by E, of course, it's the same thing as multiplying on the right by E. But also, if I multiply on the left by S, then that's the same thing as multiplying on the right by S. And if we double check with our, let's see what this was. And if we double check with r squared, if we multiply on the left of that subgroup, then e times r squared gives me r squared. And s multiplied on the left by r squared also gives me sr squared. Even though it used to be on the left, that's the same thing as it being on the right, specifically for r squared in D4. And so we get the same thing over here. And then with SR squared, the same sort of thing happens. And then you'll see that this group eventually, when we get to down here, they just ended up checking one element. And it does suffice just to check one element within there. So down here, when checking if R squared and SR squared, the subgroup generated by those two things in D4, when they check the left coset where you multiply by R, they get these four elements. They checked when you multiply on the right by R, so they're checking each one of these things multiplied on the right by R. We get the same thing as multiply on the left by R, just in a different order, but that's okay. And that's good enough just to check one of those elements that's already in there, because we know another name for this is also going to be like SR multiplied on the right. And so if SR is showing up in the right one, and SR is showing up in the left one, then we know that SR times that subgroup, that left coset, is also the same thing as that right coset, just by the nature of it showing up in both. But we had to check, first of all, just with the R right there. So it worked out with one of them, so it's going to work out with all four of them that are already appearing in there. Okay, so then once you checked both of those last time, then you take a look at the subgroup generated by S in D4. We want to know if that's normal. They had a question mark here. And you already checked the E, and you already checked the S. And so those ones end up being exactly the same. But when you check the left coset with R, and the right coset with R, we get different elements. So over here with the left coset, RS gives us SR cubed, but multiplying on the right of this S gives us SR, which is not SR cubed. And so these are not the same set, and so these are, this subgroup is not normal in D4. And so we don't have to check the rest. We already got one where it's not going to be equal, and so it's not normal. And so I had briefly mentioned right before the break that one way that we could have shortcutted this was by the fact that these first two ones, so this one and this one, the index of this group within this group is 2. This subgroup had size 4, and this subgroup had size 2, so 4 divided by 2 was 2. And this group had order 8, and this subgroup had order 4. 8 divided by 4 is 2. And in fact, this always happens whenever you split up so that you just have the original set. What's left to go in either the left or right cosets is just the remaining half of the elements. There's no other choices. So because there's no other choices for the left one, there's also no other choices for the right one. And anytime that we have index 2, then we get a normal subgroup automatically. So you could have, like on the final, skipped a lot of this work with a very special theorem. So if, let's get rid of that X there. So theorem 5.33, suppose that G is a group, let H be a subgroup of G such that the index of H in G is 2. So the order of G divided by the order of H if we have finite groups. If that ends up being 2, then H is a normal subgroup of G. All right, so that's about where we left off, and that's all the more that we're going to say about normal subgroups beyond the thing that you're proving for the final project. So you can pause the video, see if anybody has any questions, and if so, have somebody post them on Perusall for us. All right, so hopefully you unpaused me. Otherwise, I guess that was a really short class and nobody's listening to me anymore. But let's go ahead and we're going to jump into what you watched the video on about direct products. There was like 8 minutes. I'm just going to look at the textbook. But if you had questions about the video, you already could have asked those on Perusall, but now you can also just ask them on this video on Perusall. So we have the direct product. It's showing up in your book, and you watched a video all about it. But in general, what we have is, I guess we'll just write down this one thing for your notes. I know that you already have a whole bunch of stuff, but let's just write down the gist of what we're trying to say. So the gist of what theorem 6.1 is trying to say is that if G1 and G2 are groups, I know that in the book it uses G and H, but it pretty quickly shifts to G1, G2, G3 later on. So I'm just using G1 and G2. So if they're groups, then take that Cartesian product that you learned about whenever you start learning about sets. Then G1 cross G2 is a group. So this thing here in algebra, we're calling the direct product. We're no longer just calling it the Cartesian product, we're going to call it the direct product to say that we're putting a little bit of extra structure on it. And each of these things is a factor of that direct product. So G2 is a factor and G1 is a factor. So it is a group in all of the various ways that you would expect. And it's basically, as you saw in the video, we take the group operation from G1, and anything in that first component, we do the group operation from G1. Anything in the second component, we do the group operation for G2. The identity of this group is the identity of G1, comma, the identity of G2. The inverses are the inverse of the element in the first slot, comma, the inverse of the element in the second slot. So I'll point out a few other things from the book, and then you can feel free to ask each other questions about the video if you have them. So let's look at the book briefly here for some of the things that you wrote down. There's a few things here that you didn't write down, and you don't need to write them down now either, but I just wanted to point them out. So for any of these, if you didn't already have them written down, then don't scribble them down. I had you write down already the ones that I thought were important enough to write down. Okay, so I think something that you didn't write down that hopefully should be somewhat obvious after we're done talking about direct products today is that G1 cross G2, we can always form an isomorphism with G2 cross G1. The cross is just saying, the direct product is just saying that we have something from one group, comma, something from the other group. We could just, hold our group up to a mirror and then say, hey, everything's still working out in those components. We're going to get all of the same structure, whether the components are in front of the comma or after the comma, as long as we're being consistent. Also, if you take an identity from really any group, but here it says from G1, and you do that set cross G2, then that is just going to be isomorphic to G2. So if I had something like G2 was equal to the, let's say the rotation group on the triangle, then we have our elements are just going to look like E1, comma, E2, where E2 is just the identity in R3, E1, comma, R, oops, E1, comma, R squared. And so how would this group work? Well, in the first component, no matter what operations you do, you would just get the identity in that component, and you'd be doing all of the work in R3. So putting that identity in front of there and putting the fancy parentheses in front of all the elements and after all the elements doesn't change the group structure of R3. So if you direct product just with an identity element, then we're just isomorphic to G2, and it works the other way around too. All right. So this notation here, that just means to take a product, and so we have a product of a whole bunch of sets. Then this notation just means A1 cross A2 cross dot 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 AN. So it's just a big product symbol. And we, instead of just having A1 comma A2, now we can have A1 comma A2 comma A3 comma A4 all the way up to AN. Then in the video, it talked about you can extend the direct product to as many of these places as you want. So you'll do the operation in the first component, and so you'll get A1 and then operate times B1 with whatever group operation you have there. And then you'll take a look, okay, let's do A2 times B2 using whatever that group's operation is, and we'll get that in the second component, and then all the way up to the last one and everything in between. So there is our direct product. Also in the video that you watched, we have that the order of the group that we're forming with the direct product is equal to the order of each of the individual groups multiplied together. And so hopefully that's pretty understandable. If not, then when I ask you to pause the video, you can talk with each other about why that is. That group is infinite if and only if at least one of the individual groups is infinite. So if one of those individual groups was infinite, then the whole product's going to be infinite. If every single one is finite, then the whole product is going to be a finite number of elements. Then we have this important theorem down here. If all of our groups involved in that direct product are abelian, then the whole thing is abelian. So the product of all of those GIs is abelian, if and only if each one of those individual groups is abelian. So you have a quick way of knowing, like if I ask on the final, is this group that is a factor group, direct product group, if I ask if it's abelian, and all you have to do is look at each of those individual groups, and if you find one that's not abelian, then you know the whole thing's not abelian. Otherwise, you have to show that they're all abelian, and then the whole thing's abelian. Okay, so real quick, and then I'll ask you to pause. So we had this one example Cayley diagram of Z4 cross Z2, and so you can see what each of those elements looks like. So we have the identity is 0, 0, and then we have a whole bunch of other elements. The things in the first component come from Z4, so you'll find anything from 0, 1, 2, or 3. And the stuff in Z2, well, that's just 0 and 1. So the only things that you'll see in the second component are just 0 and 1. And so you'll see when we take 1, 0, that apparently is the orange arrow, because that's how we get from the identity to 1, 0. And so to take 1, 1 plus 1, 0 gives me 2, 1. I just do the 1 plus the 1 and the 1 plus the 0 in each of the individual components. So how about go ahead and pause the video here real quick and talk with each other. Was there anything from the video that you watched, and was there anything from just now that you remembered? Oh, I had a question about how that worked, or I thought that was clear, but now I don't get it. So talk with each other about that. If you can't come to any sort of conclusions, then post something on Perusall, or have the video stopper post something on Perusall. And once you're all good, then we're going to have a presenter present problem 6.9. And so I'll email somebody ahead of time, or if nobody got an email from me, then you guys can just pick somebody to send up to the board. But I want them to put their diagram on the board, on the whiteboard, please. And so you can find some things to do while they put that picture up. You can talk with each other about the products and all that. And I will only answer, once you unpause the video, what that Cayley diagram looks like. Otherwise, I leave it up to you guys to come to a consensus about whether it's abelian, whether it's cyclic, and what group it's isomorphic to. And so hopefully there's some good debate about that, and you can all come to a conclusion. So pause the video now, talk about any questions that you have for direct products, and then have somebody present 6.9, and when you're all done with all the parts of 6.9, then come back here. Okie dokie. So let's go ahead and let's take a look here at what your diagram should sort of look like. So there are a few possible answers, but in general, you probably have a triangle and another triangle, or it could be changed into a triangle and another triangle. And it looks sort of like D3, but the arrows for the one triangle are going in the same direction as the arrows for the other triangle. And then you have these sets of elements with the other color of arrow, where you have that element that the 1 came from Z2, and it's just going back and forth with that green arrow. So post any questions that you might have about if this diagram is the same one or a different one than what you have, and whether those differences are significant, and talk with each other. And then once you're done talking with each other, then let's go ahead and move on. After you've come to a conclusion about whether you guys had the right Cayley diagram, then I want you to work on, at the board, don't let anybody just sit there and do it in their notebooks. Have everybody get up to the board and draw some pictures on the board, please. Do 610 and 611 in groups. Try to make your groups small enough that nobody's just sitting there not sure what to do. Make sure everybody's included. Be inclusive of each other. 610 should be pretty quick. And 611 is a little bit slower, but still kind of quick once you know what you're doing. But notice you need to find a generating set first, and then create the Cayley diagram. It might be helpful if you decide as a class what that generating set should look like, especially based on what you did in 6.9, before you make your diagram. But go ahead and pause me for a while and work on 610 and 611. And once it looks like about 60 to 80% of the groups are nearing completion, then start winding everybody down, compare each other's diagrams, and then compare with me in a little bit. All right, I'll see you in 5 to 13 minutes. Okay, so hopefully you got your diagrams, and I will take a look at what you have. What I want you to do is you're going to share those diagrams as if it was a daily homework. So whatever you had, take a picture of it on your phone, and then throw that up on Brightspace for me to look at before Wednesday, and we'll see what you came up with. Okay, so once we have all of these diagrams, hopefully you have a lot to look at on the whiteboard, then we want to look at, I think it was the last theorem that you wrote down here, about the order of an element in a direct product. So let's take a look at the groups that we have in our Cayley diagrams before we move on to that theorem. All right, let me just get my thing up here. Okay. So let's take a look at the order of the element 1, 1. Now, hopefully you already discussed the order of an element like this when you were going over 6.9. Hopefully you did, because it kind of reveals something about the group. Okay, so let's look at 1, 1. So how is 1, 1 formed? It's not one of the generators. Well, it's either a green and then a blue arrow, or it's a blue then a green arrow. It's an abelian group, so we can do either one. I'm going to do green, blue each time. So green, blue, we get to 1, 1. Green, blue, okay, we've gone 2 times, adding 1, 1 to itself. Green, blue, that was 3 times. We're not back to the identity. Green, blue, that was 4 times. Still not back to the identity. Green, blue, 5 times. Green, blue. Okay, so it took 6 times to get back to the identity. So the order of 1, 1 is 6. Now, versus, and I'm just going to do a different slide. There's not going to be much here, but hopefully you have these on the whiteboard that you can look at. If you look at the order of 1, 1 in your diagram for Z2 cross Z2. So shout at me through the projector screen so I can hear this all the way in the car, probably. I'm probably in the car somewhere between Pennsylvania and New York at this point. What's the order of 1, 1? Yeah, I bet nobody shouted. But the order of 1, 1, if you look at your diagrams, is 2. If you don't see that, pause me and discuss. How about the order of 1, 1 in Z2 cross Z2 cross Z2? Oh, so not 1, 1, but 1, 1, 1, 1. The order of that element in Z2 cross Z2 cross Z2. Then the order of that is 2. And in fact, the order of like 1, 0, 1. Oh, there's way too many. Okay, parenthesis and then line. Okay, the order of 1, 0, 1 is 2. So what's going on here? Why do I only have, oh, and if you don't understand where these 2's are coming from, then pause and look at the diagrams. Hopefully you're talking with each other. Hopefully you pause me. Okay. So 1, 1 had like the special property in Z2 cross Z3, and it only goes 2 times around until you get back to the identity for these groups. So what's going on? So 1, 1 had a special property in Z2 cross Z3. And let's take a look at why that is. We actually already discussed it when we talked about permutation groups. So in those permutation groups, we had Isabel and I pointed fingers around like a square and a triangle for these different cycles that were going on. And it's the same sort of thing that is happening in this group. It's not a square and a triangle. It's a thing of order 2 crossed with a thing of order 3. So the 1, oh, wrong color here, from the first part of 1, 1 is in Z2. And every other time, it's going from 1 to 0, and then, oops. So we went from 1, 1, so green, blue, so back to 0. Green, blue, back to 1. So it's cycling between 0 and 1 each time we add 1, 1. But this one, every time we add 1, 1, is cycling between 0, 1, and 2. And so we go 1, and then we go 2, and then we go back to 0, and then back to 1. And so that 2 and that 3, the first time that going every 2 and going every 3 line up is the least common multiple, just like we saw in those permutation groups. And so we see that the order of 1, 1 is equal to the least common multiple of 2, the order of the first element, comma 3, the order of the second element. In Z2 cross Z2, the order of 1 in Z2 is just 2. So that came from the least common multiple of 2 and 2, which is just 2. And each of these came from the least common multiple of the order of each of these. We had 1, 1, and 1. So we had order 2, order 2, order 2. So that was just 2. And then the least common multiple of 1 has order 2, 0 has order 1, and 1 has order 2. The least common multiple of those numbers is still just 2. And so it's the least common multiple. The first time that all of these are wrapping back around to the identity, it's going to depend on that least common multiple. So that's where we get that theorem 612 that you already wrote down. So let's go back over to that real quick here. So suppose that G1, G2, all the way up to however many groups you have, Gn, they're groups, and let little g1, little g2, little gn be in that direct product. then if each of the orders, if we call them Ri, so it's really easy to lose track when you're reading this theorem for the first time what these R's are. It's just the order of this. We just didn't want to have to write these bars every time. But read it as the order of each of those group elements. Then the order of this new element in the direct product is just the least common multiple of each of the individual orders of the individual elements. So what I want you to do is I want you in your groups or in your partnerships or whatever the heck you're doing, whoever you're doing this with today, I want you to do 6.13, problem 6.13, and then one additional problem that I'll call D. So you can either read that off there or I'll make a slide for this real quick. So let me slide on over. Slide. Oops, didn't want to have an extra one of those. So let's just, nope, don't want to go that. Okay. All right. So A. So we want to find the order of each of these. So find the order of each of these elements. So A, we want to find the order of 6, 5 in the group Z12 cross Z7. For B, we want to find the order of R, I in D3 cross Q8. For C, we want to find the order of, now be careful with this, we have these parentheses on the inside. This was our cycle notation, specifically these are transpositions. They're disjoint cycles. They're going to be from S4. So those first set of parentheses, those are from S4, and then that 3 is from the group Z15. And then the D that I'm adding on here is going to be, I want to find the order of 7, R squared in Z8 cross D12. All right, so pause me, work with each other to find the order of each of these elements. Also see if anybody needs any help finding any least common multiples. Usually greatest common divisor is a little bit easier to find than least common multiple, but our numbers in this class are pretty small, so you shouldn't have to do anything sophisticated. But I'll be quiet. Go ahead and pause me and then come back here for what I think are the answers, but try and agree with a partner before you look at mine. All right, so here's what I got. Let me know if I made any mistakes. So pause me and see if anybody has any questions. All right, then we're just going to point out a few things about direct products, and then we're going to be done with these. So let's take a look here at a few properties to finish this out. So some things that you didn't write down, let's see here. So you didn't write down, and you don't need to write down now, that you may or may not have noticed that if you take Zm cross Zn, so specifically these cyclic Z groups, that direct product is going to be cyclic if and only if M and N are relatively prime. And that has to do with when numbers are relatively prime, then what we have is their least common multiple is just multiplying them. So the reason that theorem 6.15 comes about is because of what's talked about in corollary 6.16. The thing that it's isomorphic to is going to be exactly Zm times n. So the group Zm cross Zn is isomorphic to Zmn if and only if m and n are relatively prime. But again, you don't need to write that down. Okay, so real quick, if we have G1 and G2 are groups, and we're looking at their direct product, then what is true about subgroups? Well, one interesting thing is that if you take a look at H1 cross H2, where H1 is a subgroup and H2 is a subgroup, then H1 cross H2 is also a subgroup of G1 cross G2. So go ahead and get this written down, and I have no clue how long it's going to take you to write that down, so you can pause me, I suppose. Okay. So one thing that we want to point out, though, there we go, is that these H1 cross H2s are not the only subgroups of G1 cross G2. Now, I'm being very loose in my notation. I still mean that H1 is a subgroup and H2 is a subgroup. But these are not the only subgroups. They don't just come from a direct product. So our last thing that we want to talk about is in problem 6.21. I want you to see if you can find an example of some subgroup of a direct product such that H, that subgroup, is not a product. Sometimes we just shorten direct product to just the word product of subgroups. So we're looking for a subgroup that cannot be split up into, oh, this is just H1 cross H2. So I'm guessing that we might have gone a little bit over and you're doing this at home, so you don't have anybody to talk to, but either way, pause and think about it. All right, so the one that comes to mind immediately for me is in Z2 cross Z2. So we can always form subgroups just by taking element times itself. We can look at that cyclic subgroup. So the subgroup generated by 1, 1, then that is a subgroup of Z2 cross Z2, but it's not the direct product of two groups. So if that raises some questions for you, then write down what sort of questions you have, and then you can either ask them on perusal or bring them to me the next time you see me. I hope that you have a great day, and I will hopefully see you either at office hours or at our next time together, and I hope everything went well for you. Email me with any questions or post some things on perusal. Bye.